I'm sorry I haven't completed the revision of the first section, so I will dispute it. I think I can complete it today. Okay, so once I've done the revision, I will dispute it to you. Okay, so I will continue our discussion to derive necessary conditions when we have Fourier series representation of a periodic function. Okay, so assuming that a periodic function with period 2 pi has this representation. Okay, so which means that the partial sum function will converge to the function value of x for almost all x in R. Okay. 1. Together, further And okay, so we have shown that if we integrate, we've shown that this integral exists. Okay, we have explained that this is from the dominated convergence theorem. That this integral is equal to 2 pi a0. Maybe I say f of x absolutely. Maybe I'll integrable over and okay by the dominated convergence theorem. Alright. Now, okay. Now, furthermore, we have okay. For all k greater than equal to 1, when we evaluate this integral, so the integral is the product of the periodic function and the cosine function. Okay. Now, so right now, so this is the because of this result, so you express the periodic function f by this limiting function. Okay. Okay, and again we can exchange integration process and the moving process. We can exchange their order. So this is becomes true. Okay, so again, our code we call the dominated convergence theory as dominated convergence theory, DCT. So again, this is by DCT. Okay. So by DCT, we can exchange the order of integration and limiting process. Okay. Okay, and because the partition function is this function, right? So by the linearity of definite integral, so we have first of all A0 cosine kx dx. Okay. Plus summation f from 1 to infinity an cosine n x cosine kx dx plus bn sine nx and cosine kx dx. Okay. Yes? Oh. Sorry. Okay. Right. So this is just purely substitution. A pure substitution of the partial sum function by this formula, right? Okay. So we have this one, and by the orthogonality of the trigonometric system, right? We have presented last Tuesday in theory 11.1. We know that this integral is always 0. Okay, always 0. Okay, and this one, I'm sorry, I can move A0 to here. And we know this is equal to 0. Okay, right? Now the thing left is here. So what happened? What happened here? Yep, when n is not equal to k, we know that it's 0. Okay, it's 0. But when n equal to k, all right. Oh, by the way, I'm sorry. This is n. Okay. So we have the value 0 when n not equal to k. Okay, not equal to k. But how about when n equal to k? Okay, so we will have so when n equal to k, we have cosine kx dx, right? Like here. But from the double angle identity in trigonometry, we know that this is 1 plus cosine 2kx divided by 2. Is that correct? The double angle formula here. So, and once again, so you can see that we have 1/2, okay, pi minus pi, and dx plus 1/2 pi minus pi cosine 2kx dx. We have that one. But as we know, this integral equal to 1, again by orthogonality theorem. Okay, and so what is that? This is become the pi. Okay, this is pi. So the value is pi when n not equal to k. From n equal to k, n equal to k here. Okay? Okay, so now the n goes infinity, right? And here we will have pi. So this is pi, so we have a k pi. We make a pi and delta. Okay. Summation from 1 to n and the delta in k. Okay. if you think this is too quick, you can see here, n from 1 to infinity an pi and delta nk. Okay? Now, so if, I'm sorry. So if n going up, right? N going up, so n, when n is greater than or equal to k, okay, then we have, so let's say that this is equal to, so there is only one term left, so it's ak pi here. Okay, and so this integral is equal to ak pi. So that's why ak becomes 1 over pi and the times the integral f of x cosine kx dx. Okay? Okay, this implies that a0 is equal to 1 over 2 pi f of x times 1 dx. See. Okay, so the a0 corresponding to the constant function 1 in the trigonometric system, right? Alright, so we multiply 1 and take the integral divided by 2 pi. This is a0. But to find the ak, we actually integrate, evaluate this integral of this integral, which is f of x times cosine k pi, kx. Okay, and then divided by pi. Okay. Okay, so we can find basically an and 0. How about bn? Well, so you can and for all k greater than 1, when we compute this integral, so this time we multiply the periodic function f with sine kx. Okay, so that okay here. Okay, and once again, by the dominated convergence theorem, we can exchange the order of limiting and the integration process. So this is okay, and then linearity. Okay, so we have a0 sine kx dx plus summation from 1 to n an cosine nx and sine kx dx plus bn sine nx sine kx dx. Okay. orthogonality, we know this is equal to 0, and this is also equal to 0. But for this one, we find that it is 0 if n not equal to k. But if n equal to k, now we have the square of sine kx. So again, by double angle formula, we have minus cosine k2kx and dx here. Okay? So again, similar to here, we know this is equal to pi. So when n equal to k. Okay. Alright? So 0, 0, and so we have limit, and goes to infinity, summation n from 1 to n, bn pi delta nk. Okay? And so when n is bigger than k, then this term becomes to bk pi. Okay, bk pi. So this implies that bk can be obtained by this formula. Okay, so our calculation shows that if we assume that we have this representation, means that this series sum of functions converge to f of x for almost all x in R, which means that we have this limiting process for almost all x in R, if this is the case, and have two further assumptions, 1 and 2. These two assumptions is necessary because we want to apply the dominated convergence theorem such that we can exchange the order of integration in the limiting process. It's very important assumptions. Okay, so with that, then we can obtain the coefficients A0, An, and Bn from this periodic function directly, right? So this is the case we have. So this is a necessary condition. Right. Any questions? Okay, so we write down, so we conclude that a necessary condition for a periodic function f with a period to pi to have a trigonometric series expansion. Trigonometric series expansion f of x equal to a0 plus it's a series sum. Okay, for almost all x in R, such that the function gx equal to converges for almost all x in R, and is integrable over one period. Is that right? Is that f is absolutely integrable over this interval, and so we can write down a0 is 1/2 pi minus pi f of x dx, and an equal to 1/2 pi f of x cosine mx dx, and equal to 1, and the bn equal to 1/2 pi f of x sine mx dx, and equal to 1. Okay, and this three formula will be called Euler's formula. Okay, so when we refer to Euler's formulas, we mean these three formulas. Okay, these three formulas. Alright, and okay. Now, so this is the condition, right? When we have for all these assumptions, but without these assumptions, we can still compute these three integrals, right? When the periodic function f of x is absolutely integrable. Okay? So, in general, a periodic function with a period which is absolutely integrable, i.e. over minus pi to pi, i.e. minus pi to pi. Okay. So suppose that we have such a periodic function, okay, and which is absolutely integrable, which means that we can evaluate this integral, right? So that this integral has value which is a finite number. Then in this case, we can compute all these integrals. The reason is that, as we know, if we take the absolute value of the integral, this absolute value has upper bound the absolute value of x, right? So you can see here. So you can see if we take the absolute value on the integral, then it's upper bound by this one. But this function is integrable. So that each of this integral exists and is finite. Okay. So basically we can compute A0 and A1 and B. Okay. Alright, so in this case, okay, so we don't know whether this is true or not, or we don't know whether this function converges for almost all x. We don't know. We don't care. Just require that the periodic function f is absolutely integrable over one period of time. In this case, then we can construct the trigonometric series. Okay? So we can construct a trigonometric series. Okay? With coefficient A0, AN, BN, obtained by Euler formulas. Okay? So we know we can compute A0, compute AN, BN for all angle equal 1. So basically we can write down a specific trigonometric series. Okay, once the periodic function f is absolutely integrable over this interval, right? Because in this case we can evaluate these three integrals. Okay, because the is integrated. And so we can construct such a trigonometric series here. Okay. But we don't know whether this series converge or not. We don't know yet. We don't know. Okay, up to now. But we can write down immediately this trigonometric series. Okay? So we have to make a remark here. At this moment, we do not know the convergence property of this trigonometric series. Okay? But of course we can apply the technique we learned in calculus to test whether this series of functions converges or not for certain x. Okay, maybe in some range of x, this series converges. Okay, but you should apply the technique we learned before. But at this moment, you don't know before you do the test. Okay, but you can still write down such a trigonometric series. Okay, and this series, right? It's called, right? It's called the trigonometric series. Fourier series. Okay, generated by f. And we denote this relationship denoted as here. F of x, right, associated this trigonometric series. Okay? So whenever we write down in this notation, we know that f of x is absolutely integrable over minus pi to pi. And we know a0 is obtained by this formula, an is obtained by this formula for all n greater than equal to 1, and bn is obtained by this formula for all n greater than equal to 1. Okay? So we said we have this. So this trigonometric Fourier series is generated by this absolutely integrable periodic function. Any questions? Yes, please. Integrable, yeah.
So we don't suggest that for GX,
Yeah.
GX.
Yeah.
That one is sufficiently omitted.
Well, not omitted, we just say that because the Euler formula says that if we have all these assumptions, this is a very strong assumption, right? First of all, we know the series converge to f of x for almost all x, right? This is a very important assumption. And we have full assumption that this function converges for almost all x, and we call this function as g of x. And then the g function is integrable. Okay, so that this is saying that just repeat the condition we have here. So once we have this strong representation, then we have the necessary condition here. Okay, and we will ask whether this necessary condition becomes to sufficient condition. So the question is that if f is absolutely integrable, then of course we can use Euler formula to compute A0, A1, and beyond, and we can form this trigonometric series. So the question is that can we prove that indeed this Fourier series converge to the original function f for almost all x? Okay, so that is the big question, because we can construct this Fourier series, right? But the question is that maybe this Fourier series does not converge at all for any x, maybe. Okay, right? And even if it converges, maybe the convergent value is not equal to f of x, maybe not equal. Okay, so we have to answer both questions. if before we can for sure that this trigonometric Fourier series generated by f is indeed a Fourier series expansion of fx, makes that we can now, instead of the relations, but we can write down equality here. Okay, so we have to ask the questions. Okay, and so let me write down. Okay, so maybe so question raised. So they are two questions. Okay, to be raised up. The first one is the convergence problem. Maybe I write here. So the question is, does the trigonometric Fourier series, okay, generated by f, right, converge at maybe some point x in one period. Okay, so when we select a point in this period and we ask whether when we substitute a particular x here, so this is become to a numerical series, and then we will ask whether such a linear series converge. So this is called a convergence problem. Okay. Of course, we want to test the convergence problem for each x in this interval, right? For every x in each interval. Okay. And the best result will be for every x in this interval, the trigonometric Fourier series converge to a value. Okay, that is the best answer. But maybe there are some not perfect answers, says that probably except some points, right? All other points, or for all points, the trigonometric Fourier series converges. That is not too bad, right? That's not too bad. So, but we have to answer the problem here. The second problem is called the representation problem. If the series does converge, okay, at a point x in one period, x, it's a sum f of x. The sum, because we call the converging value of our series as the sum of the series, right? So if the series does converge at a point, we want is its sum f of x. Okay, so it's called the representation problem here. Okay, before we answer both problems, I would like to take an example. Okay, so consider a periodic rectangular wave, okay, with the fundamental period 2 pi. Okay, so that okay, so the function, because it's a periodic function, is period 2 pi, so I just specify the function within one period. And f can be arbitrarily defined at x equal to 0 and pi. Okay, so it can be arbitrarily defined, and maybe I will select, say, this value at 0 here, and the value here. Okay, so now okay, so this is becoming a periodic function. Okay. Alright, and it can be seen f of x is absolutely integrable over minus pi to pi. Why? Since if we evaluated that, then exceed that, so this is okay, and the value is 2 pi, which is finite. Okay, so it's absolutely integrable. Okay, even though this function is not continuous function, right? It's not because the discontinuity is at the integral multiple of pi. So you can see that, so even though it is not a continuous function, but we can still integrate it over one period. Okay, so okay, and so that and by Euler, so we can apply Euler's formulas. Okay, so we have A0 and you can see that if we integrate over one period from minus pi to pi, you can see the integral is 0. Okay, so of course this is 0. Okay, this is 0. And the ln 1 over pi f of x cosine nx dx. And so, as you can see that if you ignore the point at 0 and at pi minus pi, the f of x is an odd function. But the cosine function is an even function. Okay? So an odd function multiplied with an even function becomes to an odd function. So if the integral is an odd function, the integral is 0. Because we integrate over from minus pi to pi. Okay? So this is 0 again. Alright? And now Bn. Now f of x is odd function except if the 0 and the minus pi and pi. And sine function is also an odd function. So the multiplication of two odd functions together becomes an even function. And as an even function, then this integral may not be 0. Okay? So we have to evaluate them. And so you can do it and because it's an even function, so that we can integrate only half of this integration period. So you can integrate from 0 to pi. Okay? 0 to pi, and but you have 2 here. And under 0 to pi, the f of x is equal to 1. Here 1, right? So that, let me find it. Okay, so this is become 2 0 to pi and the sine nx dx. Okay, becomes much more easier here. And now you can use the antiderivative. Minus. Okay, we can use the antiderivative. And 0 here. Antiderivative. Remember, n here is greater than 1, so that n will be 0. Okay, and so you can have 2 and n pi, and 1 minus cosine n pi. Okay. And as you know, when n is an even number, this is 1, 1 minus 1 is 0. But when n is odd number, cosine n pi is minus 1. So 1 minus 1 is 2. Okay. Right, so that we can have 0 over 4 divided by n pi. And if n is an even number, if n is an odd number, okay. All right, so now, the trigonometric Fourier series generated by the periodic rectangular wave, okay, is what? Its summation k from 1 to infinity 4 divided by 2k minus 1 pi, and the sine 2k minus 1 x. Okay. So this is the trigonometric Fourier series generated by this periodic square wave. Okay, periodic square wave. Yeah. And at this moment, we don't know whether this series of functions converges to, right? All right, so we have to check them. But anyway, we have that. So let's take a break for 5 minutes up to 2:25. Okay. Okay, so now we will deal with the convergence problem as well as the representation problem. Okay, but to give a partial answer, then we need the following lemma. The following theorem. And this theorem, okay, is usually called the Riemann-Lebesgue lemma. Okay, Riemann and Lebesgue are two great mathematicians in history. So you can see with both going in together, so you can see the importance of this lemma, right? Okay. And I will state it here properly. So let I be an interval. Okay? Can be bounded like minus beta pi, unbounded like from 0 to infinity, right? Or open, or closed, or half open. Okay, so there are a lot of intervals. Okay, open interval like this is open interval. This is closed interval. This is half open interval. And these three are all bounded interval. But this is unbounded. Okay? Right. So help you understand all these terminologies. So in the real line, now assume that f(x) absolutely integrable over I if we integrate the absolute value of the function over the interval I, the result is a finite number. Okay? Then, for each beta in R, okay, we have the limit as alpha goes infinity over interval f of x multiplied with sine alpha x plus beta and the dx. Right. So if we evaluate this integral over an arbitrary interval I, and you can see that f of x is multiplied with a sinusoidal signal, right? And the phase beta can be fixed, right? So beta is the phase of the sinusoidal signal, okay? And alpha actually is the angular frequency. Do you know the terminology? This is called phase, and this is called the angular frequency, okay, of the sinusoidal signal. So we increase the angular frequency alpha to infinity, Okay, when we do that, this indigo become to 0. Okay, I give a proof in the lecture notes. So let me see it. Please see the lecture notes. Now I want to give you heuristic observation, okay, about why this is true. Yeah. Why? Because this is corresponding to communication systems. Because this is called modulation. So in communication system, later on maybe in your junior year, you will take a course called communication systems. And if alphabetics is the message signal, for example, the voice signal, okay? And before we send our voice signal over the air, so we will speak at a radio station, okay? And the microphone will speak then, and then the radio station will transmit the signal over the air, right? And then all the listener, maybe in car or in the house, turn on the radio and know which station, like before we have Tsinghua station, radio station, but I don't know whether it's still operated or not. But I think before, maybe 20 years ago, our EE department ran a radio station called Tsinghua radio station. And then before we send the voice signal is low frequency signal. So we will convert the frequency to high frequencies. So for example, the angular frequency corresponding to a frequency maybe is 100 megahertz. You know, 100 megahertz is about ICRT in Taiwan. Okay, but in Hsinchu there is a famous station at 90.7 million hertz. It's a pop song station that they usually play popular pop songs, the Chinese pop songs there. Okay, and so that this is called to up-convert the frequency to high frequency. So at high frequency, that we can transmit our signal in long range, right? Because it's compatible with our air conditions. Right? Because if we send a low frequency like my voice, okay, then even I scream up loudly, if you stand 1 kilometer from me, you can't hear anything. So if don't up-convert the frequency, then you can't transmit a long distance. So this is the principle of radio signals. And the basic of the broadcast systems. So they lay on the foundation of communication systems. Okay, so this we call modulation. We modulate by using high frequency sinusoidal signal to up-convert a low frequency signal to a high frequency, and then to transmit over the air, and at the long distance at the receiver, we down-convert by multiplying with the same frequency signals, and then by filtering, we can obtain the low frequency signal played by our speakers. Okay, so that is the basic system we have. And the thing is that the marvelous thing is that if the angular frequency goes to infinity, no matter what kind of function you have, may be very complicated. The only requirement is that this function is absolutely integrable, okay, over I. In that case, this is going to 0. So the meaning want to give you the idea from some pictures. Okay? So now, suppose I have a box here. Let me just consider a period of time. Suppose that, so this is our interval. So suppose that f is a constant. It is constant. Okay, and if you have, so when this is constant, so alpha is 0, then this is the 0 frequency. Okay, and okay, so like now if it's a constant, if this is a constant in this interval, now so you can see that, you can see this is the over x and sine alpha x plus beta and dx. Okay, so this is becomes true sine alpha x plus beta dx. Okay, so after multiplying with the sinusoidal signal, you can see and like depending on the phase, so you will see here like the okay, and for one period you can see here, because this is flat. So when you integrate over this period, it becomes 0, right? This is 0. So they will cancel each other, cancel. So the only thing left will become to the residue may be here, okay? Maybe here, right? Because if one period they will cancel each other. So that this integral become the area in here. Now, as alpha go up, it becomes to near, right? Because when the angular frequency go up, the period goes down, right? Goes to 0. So that the residue becomes smaller and smaller, and then become to 0. Right? So this is the reason why we have like that. If it's a constant, right? So if this is 1, but how about if f is not, say here, like that, okay? So f of x is like here. Now after the modulation, all right, so this becomes the envelope, we call envelope, and then I have okay, and okay, so this is f of x sine alpha x plus beta. Okay, this one. All right, and if the alpha becomes very big, you can expand the time scale, right? And if we look at an infinitesimal time interval, that the envelope becomes to a constant. Okay? Become to a constant like this one. So at that small intervals, just like they will cancel each other. Okay? They will cancel each other. So that they will cancel each other. Okay? And the residue becomes to here and here. Again, as alpha goes to infinity, the residue becomes much smaller and approach to 0. Okay, so that the envelope and when you multiply with the sinusoidal, you get the result. Okay, so this is the intuition that why the Riemann-Lebesgue lemma is true. All right, and a rigorous proof is given in the lecture, my lecture notes. Yeah. So I don't want to cover it because it takes time, okay? And our whole point is not in such a proof. Okay, so the idea is like that. I want you to know, that, okay, the heuristic, why this is true. And when you come up with the communication system, maybe 1 year later, we learn it. Then you may get more insight, okay, about modulation. Okay, so this is the Riemann-Lebesgue lemma. So now we apply the Riemann-Lebesgue lemma to answer our question. So we first consider the convergence problem. Okay. Now the partial sum function the partial function xn of the partial sum function xn of the trigonometric Fourier series generated by f, okay, has the following integral representation. Okay, so here let's compute it. Alright, so this is A0 plus summation n from 1 to n, an cosine nx plus bn sine nx. Okay, so this is our partial sum function. But sixth, this is the partial function of the trigonometric Fourier series, so we know the coefficients are from integration over the function f. Okay, so we can see that after so for example, this is 2 pi. Okay, here, and alright, so this is 1 over pi f of x, okay, and the cosine nx and y, maybe I will use t, okay, yeah, because x has been used, so I use t, I'm sorry, okay, so So f of t cosine nt and dt, okay? This one. Okay, so this is an, yeah, together and cosine nx, okay, plus 1 pi, maybe I include 1 pi here, it's much better, okay. So this is that. This is Bn. Okay, this is Bn and the sine nx. Here, we just plug in, okay, all your formulas, okay, into the expression. All right, and then put together because they're all integral over the same period. Now we have 1 over pi as common factor, and pi minus pi to pi here, and they have the same f of t. Okay? Now here, and the dt. Okay? So we put everything together. Okay? This is our purpose. And what is that? First of all, well, this term, this is 1/2. Okay? This is 1/2. Corresponding to this term. The other thing is plus summation n from 1 to n. And this is cosine nt, right? Cosine nx, right? Plus sine nt and the sine nx. Is that okay? Together? And with the sum difference identity we had before, what is that? This is cosine n t minus x. Or x minus t, that's fine. X minus t. Okay, so now the partial sum function has this integral representation. It's f of t, okay, and with this function, cosine n x minus t, okay, and dt. And we define this term, okay, call is d sub n. Oh, because they have n terms, I'm sorry. D sub n of x minus t. Okay. So this has become to a kind of convolution, okay? A convolution over one period. Do you know convolution? Do you have any convolution integral? Convolution of two functions, f of x and g of x, okay, over an interval. The convolution integral is like here. Okay, over I. Do you know that? If you know this term, please raise your hand. Oh, okay, thank you, great. So this is just like a convolution integral, all right? Okay, and so this is the, this function, all right? Define function, and this is called the Dirichlet kernel. Okay, so dmx defined to be 1/2 plus summation n from 1 to n, and the cosine nx. Okay, right, so this one is called Dirichlet. Alright, so Dirichlet's kernel. So D indicate the mathematician Dirichlet. Alright, so this the kernel here. And so you can see the kernel, this kernel function is also a periodic function with a period 2 pi again, right? So you can see here. So this is, so you can simplify this sum by a technique you may learn in high school, okay? And this is become to sine function n plus 1/2 of x divided by 2 sine x divided by 2. Okay, if your x is not equal to 2k pi, k is any integer. But if x is 2k pi, when x is 2k pi, then we know that this is 1, right? This is 1. Okay, and so we have n plus 1/2. Okay, because when x is 2k pi, this is k pi, and the denominator becomes to 0. So this is a singularity. Okay, all right. So this formula here. It is easy to prove. Why? Well, you multiply the Dirichlet kernel with this denominator. You multiply them, and applying product to difference by cancellation, you get this term. You can try it. Okay, and so it's easy to prove. You multiply this sum with the denominator. You multiply them. Okay, and we will get the numerator after some cancellation. You can apply the product to difference formula in trigonometry. Okay. Okay, so that the partial sum function can be represented as a convolution integral. Okay. Okay, now since the both f and the Dirichlet kernel are periodic functions, okay, with the same period, 2 pi. So we can replace the interval of integration x minus pi, x plus pi. By moving the interval with the constant x, okay? So if x is positive, we move the interval to the right. If x is negative, we move the left, okay? Okay, so, alright, and right, so now we have, remember this pi f of t Dirichlet. Okay? So if x is fixed, okay, if f is fixed, okay, now this is the convolution, and because f and dn, both of them are PRI function, so that because this integral is over one period, okay, so now you can shift the integration interval into this one period. Okay, and then we can do the change of variable. So the change of variable is here. So we do that. The change of variable, okay, we let u equal to x minus t. Okay, so we let u to x minus t, so that du is equal to minus dt. Okay, and so 1 over pi, and here, so t is x minus pi. So this is 1 pi, and minus pi here, and f of at t becomes 2x minus u, and the dmu, okay, and du minus du here, okay, this is minus du. Right, and then we upside down the Gaussian limit, so that the minus disappear. So this is become 2, 1 over pi, 1 minus pi, f of x minus u, du. So actually, this is a common property about convolution. Okay, originally the partial sum function from there, this is 1 over pi minus pi and f of t dm x minus t dt. So we have x minus t, okay? But we can change the rho, okay? So this is the typical property of convolution, okay? So we come to here. Okay, so now we have a simple representation here. Okay. Any questions? Now, look at here. This is an even function, right? Because cosine function, even function. So the Dirichlet kernel is an even function. And this is an even function, okay? Right. So now we further developed it. Right. So here we have 0 to minus pi, okay, f of x minus u, dmu, and du plus pi pi and 0, fx minus u, dmu, and du. Okay. Now, now we change, relates u to, in here, relates u to minus v. So in here, this one, v u equal to minus v. Okay, by change of variable. So that this becomes to f of x plus v, and the dm, v, and dv. Okay? All right. And so if we return this from minus pi to 0, okay, we get the same. So this is by change of variable. Okay. Oh, sorry. Minus v. Minus v here. Okay, and because it's even function, so this is dm v. Okay, all right. So now, so we have. Oh, I forgot. This is become 0 to pi. Sorry. Okay. All right. Maybe I do it gradually by the change of variable. So vu is minus v. Okay. So now du becomes minus dv. Okay. And this is fx plus v, and the dm minus v, because u is minus v. So we have that. Because this is a minus sign, so that so we can flip. Yeah, but because of minus v, this one, right? No, because when u is minus pi, v becomes pi. Because we do the change of variable. Yeah. Okay. So that's why I want to do it step by step. All right. And when we remove the minus sign, we just flip. We just flip the equation limit. So that, okay, so we have that. Okay, so this true integral has the same integration limit. And by the even function property, this is equal to dmv. Okay, and so now we have that we can do it. We have 2 here, and divide by 2 here, and the dm okay. All right, so now we don't need this parenthesis here. Okay. So now we can evaluate into this one. So the partial sum function now can be represented in this integral, okay, with the Risley kernel here. Okay. Now. Now, so from here, the partial sum function converges, okay, converges at the point x in a period, okay, if and only if, of course, the following limiter exists. And goes to infinity, right? So that the following exists, and so that is the integral representation. So this is 2 divided by pi and 0, and f of x plus t plus f of x minus t divided by 2 here, and the Dirichlet kernel is here. Okay, so if x is not equal to the even multiple of pi, okay, then we have this formula. So we can write it down. Sine n plus 1/2 t and 2 sine half and dt. Okay? Is that okay? Right. And the 0, because we get the integration, we can think about that it's integral, we don't include the endpoint 0, because when this is 0, then it blow up, right? So, but for the integral, right, if that we can, for a point, we can just exclude one point, that's okay. Okay, so we still have this one. Okay, and now so the Poisson function converges at a point if and only if that this limiter, right, exists. So we can replace by t. Now we want to replace, as you know, sine theta is approximately equal to theta, right? When theta is very, very small, okay? So when theta is very small, the sine theta is about the theta, okay, about theta. And so pure sine t divided 2 is about t. Okay, if t is very, very small. Okay, very small. So this is our knowledge about that. And so here, even though t is not small, but the dominating thing is that when t is small, then the numerator becomes quite small, and so that this term will dominate because it's become a very big term. Okay, and So now we want to show that they actually, when m goes to infinity, we want to show that this limit will go to here. So we want to show that. Okay, we want to replace the denominator by t. Okay, now why? Since okay, so now the difference. Since the limit. Over t minus 1 over 2 sine t divided by 2 and f of x plus t plus f of x minus t 2 and the sine and plus 1/2 of t. Okay, and dt. Okay, so look at here. This limit as n goes up. Now we look at the Riemann-Lebesgue lemma. When we look at the Riemann-Lebesgue lemma, this function. So this function as h of t, see here, okay? So h of t times the sinusoidal signal, and when the angular frequency goes to infinity, this goes to 0, right? If this function is absolutely integrable, right? It's absolutely integrable. So by Riemann-Lebesgue lemma. As can be shown that okay, so I'll stop here, and so next week I will show to you that this ht, so this one is absolutely integral. It means that we can evaluate the integral and which is finite, so that we are able to apply Riemann-Lebesgue lemma that to show that the difference of these two limits. Okay, the difference of these two limits, right, is 0. So that we can replace the denominator function to be this simple function. Okay, right, and and we will be very close to our answer. Okay, very close to our answer. So, all right, so we have to check that this is indeed absolutely integrable. Okay, so any questions? Right, so I'll stop here and I'll see you next Tuesday. Okay, and I will assign homework, okay, for you to do.